MRSA is a bacteria that can cause diseases that are pretty much fatal. Researchers have found a set of new antibiotics that can kill a drug-resistant bacteria that kills over 121,000 people in the world every year. They did this by using deep learning algorithms through the use of AI. These compounds were shown to be able to kill MRSA grown in a lab dish and in 2 mouse models of MRSA infections in a study that came out today in Nature. These compounds are also very safe for human cells, which makes them great candidates for medication. The dataset used to guess how well a drug would work was the magic behind the discovery. Researchers could use this information to make new drugs that work even better than the ones found by the model, which has been pieced together over time. The big idea here was that we could see what the models were learning that helped them guess which molecules would make good medications and which wouldn't. With further research, medications could be tailored to your very DNA, allowing your system to heal itself more efficiently. Our work gives us a framework that saves time, resources, and insight into how chemical structures work in a way that we haven't had before, states James Collins, Professor of Medical Engineering and Science at MIT's IAMS and Department of Biological Engineering. The study is part of the Antibiotics AI project at MIT. This sounds like a brilliant idea, as it has already been shown that AI can perform tasks that doctors can't. The research leads are Felix Wang, author, and Erica Zheng, former graduate, who was mentored by James Collins. AI predictions. This disease leads to skin problems or pneumonia, sepsis, which can be deadly. Collins and his partners at the Jameel Clinic have been using their deep learning techniques to look for new antibiotics for a few years now. Their work has resulted in a set of compounds that could fight Acinetobacter baumannii, as well as other antibiotic-resistant bacteria. AI finds chemical structures that are linked to the antimicrobial actions. From here, they then search through millions of compounds and through probability calculations, come back with a set of data indicating which compounds are best suited, worse suited, etc., to fight the bacteria at hand. As Wang quoted, "The goal of this study was to open the black box. What this means is to uncover exactly how deep learning has made its assumptions and choices using the data it was supplied with. These models are made up of a huge number of calculations that look like neural connections, and no one knows what's going on inside. Your model can show almost any molecule as a chemical structure, and you can also tell if that structure is antibacterial or not. The models have been fed data from a lot of case studies. If you give it a new molecule with a different set of atoms, etc., it can tell you how likely it is that that substance will be antibacterial. Algorithms using what's been named the Monte Carlo tree have been modified to figure out how the model was making choices. This very same algorithm has been used to help make other deep learning models, such as AlphaGo, etc., easier to understand. This reverse engineering of the data lets the model not only guess how effective each molecule is at killing microbes, but also guess which parts of the compounds are most likely the cause of their effectiveness. Potent and promoting. The researchers taught 3 more deep learning models to guess whether the compounds were harmful to 3 different types of human cells. They then narrowed down the list of possible drugs even more. Scientists found compounds that could kill microbes while having few bad effects on people by putting this knowledge together with predictions of antimicrobial activity. Researchers looked at about 12 million chemicals, all of which are sold in stores using this set of models. Based on chemical substructures inside the molecules, the models used this collection to find compounds from 5 different classes that were thought to be effective against MRSA. The researchers bought about 280 compounds and tried them against MRSA that was grown in a lab dish. This helped them find 2 compounds from the same class that looked like they would make great antibiotics. Each of these chemicals cut the number of MRSA bacteria by a factor of 10 in tests with 2 types of mice, one with an MRSA skin infection and the other with an MRSA systemic infection. The chemicals seem to kill bacteria by making it hard for them to keep an electrochemical gradient across their cell membranes, as shown by experiments. This gradient is important for many important cell processes, like making ATP molecules, which cells use to store energy. Halicin, an antibiotic possibility found by Collins's lab in 2020, seems to work in a similar way, but only against gram-negative bacteria, bacteria with thin cell walls. MRSA is a gram-positive bacteria, which means its cell walls are thicker. There is a lot of proof that this new structural class works against gram-positive pathogens by selectively removing the bacteria's proton motive force, Wang says. Scientists say that the molecules only hurt the cell membranes of bacteria and not human cell membranes in a big way. With our greatly improved deep learning method, we were able to predict this new structural class of drugs and confirm that it does not harm human cells. The experts told Ferrobio about what they found. Collins and others started Ferrobio as a non-profit as part of the Antibiotics AI project. Now the charity is going to look into the chemical properties and possible medical uses of these compounds in more detail. Based on the results of the new study, Collins's lab is also working on making more drug options. They are also using the models to look for compounds that can kill other types of bacteria. We are already using similar methods based on chemical substructures to create new compounds, and of course we can easily use this method to find new types of antibiotics that fight different pathogens, Wong says. The paper was also supported by Integrated Biosciences Inc., the Weiss Institute for Biologically Inspired Engineering, and the Leibniz Institute of Polymer Research in Dresden, Germany. These institutions work with MIT, Harvard, and the Broad Institute.